So this video is for day 5 for chapter 2. We're going to be working our way towards looking at planet orbits. We need to take one day off just to review some gravity from Physics 11, and then after this one lesson, then we'll spend a couple of days looking at how planet orbits work, a nice little application of circular motion. But for now, we're just going to do a little review of gravity, and we're going to start off going with kind of the awkward equation, but it's the equation that works everywhere, the universal law of gravity. And this talks about how Isaac Newton noticed that any two objects are actually going to attract each other with a force of gravity. It does not have to be a planet. It can be any two things, and one could even be larger than the other, the way I've drawn it here. And we're going to find this mutual force of attraction, and those two forces are equal, obviously in opposite directions. That kind of is consistent with Newton's third law. And when we go to find the value for how big this force of gravity is going to be, we have to make sure we're measuring center to center. And for things as large as planets, that can actually be very, very important. So measuring center to center, we'll just call that distance r. We like the letter r because it's going to turn into a radius for a little circular orbit here in a moment. And here was the relationship back from Physics 11. A little awkward to use. This equation will tell you the force of gravity anywhere in the universe between two masses. And it involves using this universal constant, right? This number is on your formula sheet. You can use it anywhere in the universe. And if you multiply that by the product of the two masses, they have to be in kilograms, and then divide by the distance between them squared, you can actually find the force of gravity between those two objects. Played with that a little bit in Physics 11. I know normally we just go m times 9.8, m times little g. We'll get to that in a minute, but generally this is your way for finding forces of gravity. Just want to point out that this style of relationship is what we in physics call an inverse square law. It's inverse because the r's are in the bottom, meaning that if you were to have a bigger r, you're going to have a smaller force. But it's also a square law because the r is squared. So if you were to have a bigger r, the force really gets small. So for example, if you were to have a situation like this where there's some force, but then somebody said, oh, well, let's make the r 3 times bigger. The force definitely gets smaller, but it does not get smaller by a factor of 3. It actually gets smaller by a factor of 3 squared, by 9. It gets 9 times smaller. Or if somebody said, hey, I moved the objects, and the force of gravity went down by a factor of 49, well, you must have moved them 7 times farther away. If you wanted the force of gravity just to drop by a factor of 2, then you would actually make the r bigger, but only by a factor of root 2. There's kind of this square root relationship between those two things. We're actually going to use that to try to find a quick solution to this problem right here. So it says if a space station weighs, so that would be the force of gravity on it, okay, as it sits here on the Earth. If it weighs 150,000 newtons on the Earth's surface, what is its weight 4 Earth radii above the Earth's surface? Interesting measuring stick to use the Earth's radius. We're actually going to play that to our advantage here in a moment. I guess you could, and I'm not going to, but I guess you could say, well, that is mg. Why don't we go and divide by 9.8 to find the mass? Then maybe we'll find out exactly how far this is away, and then we can go and awkwardly use this equation here to find out how big that force is. But I want to show you a better way, just using our checks and arrows method. Just kind of think about this in terms of just multiplying and dividing. Originally, the space station is sitting on the Earth's surface. You can imagine, right down there touching. But Isaac Newton would say, well, measure center to center. So it's 1 Earth radius away. Later, we're going to go 4 Earth radii up into the sky. Well, that's actually 5 radii from the center of the Earth because you've already got the 1 for the Earth itself. So we're going to look at this and say, you know what? We've moved these objects so that their centers are farther apart by a factor of 5. It's gone from 1 radius away to 5 radii away. And if you can pick up on that, you've got this problem mostly finished. So the r is increased, but by a factor of 5. Okay, checks and arrows. Got my relationship here to find the force, and I know that I've actually got, the same g, same m, but I'm going to make the r 5 times bigger. That makes that denominator 25 times bigger. So this whole side over here, that whole side's going to have to go down by a factor of 25. And if the right-hand side goes down by a factor of 25, well, then the left-hand side is going to have to do that too. So this force is going to get smaller by a factor of 25. We're done. We don't even need to find the mass for this thing. we can just take the old force, divide by 25. Looks like the answer here is going to be 6,000 newtons. So that's just kind of playing off that inverse square law, thinking about how whatever change you make to the R, you see the square of that show up to the F, or whatever happened to the F, somebody must have done the square root of that change to the R. So if they said, oh yeah, the force went down by 25, factor of 25. Okay, the R went up by the root of that, by root of 25 or 5. Okay, let's try another one out. Let's start mixing some vectors together here. Let's say there are these three objects. They're pretty large in mass, 200, 150, and 450 kilograms. And you've got the spacings there measured center to center. And the request is that we find the total, vector total, force of gravity acting on that blue one due to the other two, due to the green one and the pink one. So I'm going to start thinking about the life of that blue mass there. And there's going to be some forces acting on it. One of them will be this one here. For the lack of any better way of describing it, I'm going to call that F12. That's the force that happens when objects 1 and 2 see each other and pull on each other. Now, it is only because of my own laziness that I don't bother drawing in the other F12, right? Because they mutually pull on each other. But to be honest, I just don't care about the green one. I care about the blue one. So just out of my own laziness, I'm not going to draw that in. The pink one and the blue one, they also have a conversation, a mutual conversation, and they pull on each other with a force that I'm going to call F23. And again, only out of my laziness, I'm not bothering to draw this one in. In fact, there's even another pair. There's the green and pink ones talking to each other. They're going to pull on each other as well. But that doesn't affect the life of the blue one. So let's just look at the blue one. It has these two forces, and we're going to be totaling them up, but we have to do a vector total. So if you added those two forces together, they're going to fight each other. We'll have to respect that in our math. Okay, here goes. Using that universal law, big G, just a number from my formula sheet, right, that I can go and grab, that 6.67 number, right, 10 to the negative 11, times the two masses, divided by the distance, gotta be in meters. So changing that to 0.18 meters, and it has to be squared. And when I tried that out, I had this very tiny force, 6.1, 10 to the negative 5 newtons, and it's obviously to the left. Play the same game again. That force between objects 2 and 3. I'm going to do the exact same style of calculation, and I get around 4.3 times 10 to the negative 5 newtons, and it's to the right. So it's up to us to step in here carefully as physicists and say, well, we're adding these two forces, and in this particular story, one happens to be left and one happens to be right. So we have to respect that when we add them together. We're basically adding them together carefully, head to tail. The larger one, the 6.1, 10 to the negative 5 one wins, and it's to the left. So the final answer here is to the left. Okay, so just be careful when you're asked to total up something that you know is a vector. You'll have to respect the direction there. Okay, let's upgrade this a little bit. Those two forces were nice to add because they were just left and right. But what if they were two-dimensional, or in university they might be three-dimensional? But here, let's just go two-dimensional for a moment, and let's look at this one. So it's a bit of a strange story, but it's actually a nice lead into an example we're going to do when we start looking at electric fields way down the road. So it's good practice. 4 12-kilogram spheres. Imagine it's like 4 giant bowling balls, right, are placed in a square. Imagine they're in space, so forget the Earth, right? They're just on their own. They're in a big square pattern with 4 meters on the sides of the square. That's how far they are apart on the edges. And you're asked to find the force of gravity on one of those spheres, one of those bowling balls, due to the other 3. So I need a little picture here. Imagine it looks like this. Got these 4 bowling balls in space. And they're 4 meters apart when they're in that square shape. And they've asked, can you just maybe focus on one of them and look at its life and say, all right, what's happening? What's its life like? So I'm gonna look at this one right here and say, okay, what's happening to it? And it's got a few forces acting on it. There's one above it that's pulling up. I'm gonna call that force 1, and it's kind of pulling up, to the north, whatever you want to call it, on my page. There's another big bowling ball to the right of it. So it's gonna pull it to the right, and then off diagonally is even a third bowling ball that's gonna pull on it. But it is farther away. So as it pulls on it, sure, it will pull diagonally, but it won't pull as hard because it's farther away. Now, our plan is going to be to find the values of those 3 forces, 2 of which are the same size, and then carefully add them all together. When we add them together, we're actually going to get really lucky here because the F1 and the F2, when they add together, they'll create a total that's actually diagonal up and to the right. And then F3 will just kind of add on to the end. But we can't do any of that until we find out how big these forces are. And we can't find out how big F3 is until we measure just with Pythagoras how far it is across this square. So I'm just going to do that right now. Just measuring some distances. That diagonal distance with the two 4s, just going to do a little Pythagoras there. And it ends up being around 5.6. A more elegant way to talk about it would be that distance is actually 4 multiplied by root 2. Right? That's what happens with these 45, 45, 90 triangles. It's like a 1, 1, root 2. So that hypotenuse is root 2 times bigger than the legs. All right, here we go. The size of F1 and F2 is this big. Right? Their directions are different, but their sizes are that big. As we go to find the size of force 3, it's the same game plan. You know, there are two 12-kilogram bowling balls, but they're a different distance apart. They're 5.65. So with a bigger distance apart, I'm expecting to see a smaller force. Okay, the numbers. I threw them into my calculator, and here's what I found. The first two were remarkably close to 6 times 10 to the negative 10 newtons, just a little bit more than 6. Now this next one, sure, you can just throw it into your calculator. There's nothing wrong with that, but it's kind of neat what's going to happen. The R is bigger, so the force should be smaller, should be less than this 6 number. It's actually an R that's root 2 times bigger than what we just were calculating. So if that R value there goes up by a root 2 and then you square it, that means this bottom is twice as big. And it's actually no accident that this number is exactly 1/2 as big as the 6 number. All right, final thing to do would be to put together as vectors these three forces. We have two 6's that are actually perpendicular to each other. They're going to combine with some Pythagoras, and then the F3, the little 3 here, is just waiting to get tacked on the end. So putting them together, you can go over and then up. I don't know why I went up and then over. And then the F3 on the end. So with a little Pythagoras to find that first combination, I've got the two 6's. When I put the Pythagoras to that, to find out how long that little dotted line is, I got around 8.5, 10 to the negative 10. And then the F3 just gets added on to the end of that, just 3 more times 10 to the negative 10, which would get us to like 11.5 times 10 to the negative 10, or what we can in scientific notation just call 1.15, 10 to the negative 9. Now I'm going to be a little sneaky as I present my final answer, and I'm not going to say northeast. I'm going to say towards the square center, because if I do that, I've actually given you the answer for any one of those 4 squares. They're always going to have a force overall that gets pulled in towards the center of the square. Not all of them are northeast though, so it's just a little sneaky and a little lazy where you can say, hey, you know what, every single one of them, here's the total. A force that's 1.15, 10 to the negative 9 newtons towards the square center. Okay, we've got one last thing to look at before this little review of gravity is done. It was just a quick little bit of review. I know many times so far up until today, when we've gone to find the force of gravity on cars or tables or chairs or cats or dogs or people, we've just gone mg. We've taken their mass and multiplied it by 9.8. So we should talk about where that 9.8 number comes from. And it comes from kind of looking at this picture here with my silly little cats. Some cats are bigger than others, and we might be trying to find the force of gravity on a lot of different cats sitting on the surface of the Earth. And if we were to go and use this big equation over and over and over, we would get pretty tired of having to work with that awkward equation so many times. Especially since some of the numbers never seem to change. This one's always that big G, this one's always the mass of the Earth, and this is always how far the cats are from the center of the Earth, which is always just the radius of the Earth, right? Always the same number for that part. And so what physicists did is they said, hey, why don't we just go and pre-calculate that stuff that's there in blue? And it turns out that that whole idea is the idea of a field. And so if you pre-calculate that blue stuff, maybe we'll just call it a new thing. We'll call it this gravitational field. We're going to give it a little name. It'll be little g. That number for the Earth on its surface ends up being 9.80. And you can say, oh, it's meters per second squared. Yeah, you can also say that it's newtons of gravity weight for every kilogram. Okay, so it's just a pre-calculation to help you figure out forces of gravity. So yes, on the Earth, you would take, well, you'd always take this universal number. Sorry about that, 1 second. My apologies, phone call dealt with. So looking at the Earth's calculation, we would be using this universal constant always, and then here's the mass of the Earth, and then divided by the radius for the Earth squared. If you were to try this on the Moon, you would still be using that universal constant, but you would be using the mass of the Moon and dividing by its radius squared. So this is how you can find a G value, a gravitational field strength value, on any planet or any moon. For the Earth, the number does indeed come out to 9.80. Now, we've said, oh yeah, things accelerate at 9.80 meters per second squared. But really, in terms of a field, it's a warning. It's saying, hey, there are 9.8 newtons of gravity force on every single kilogram of cats, right? So if you have a 1 kilogram cat, the force of gravity is 9.8 newtons. If you have a 2 kilogram cat, it's 19.6 newtons. On the Moon, you might have that same cat, right? Same number of kilograms, same amount of matter, but the force of gravity would be less because there's only 1.6 newtons for every kilogram of cat. So a 1 kilogram cat on the Moon would have 1.6 newtons of weight. A 2 kilogram cat would have like 3.2. Now, we're actually not going to use this gravity field for the Earth so much because, sure, we know what it is on the Earth's surface when you're 1 radius away, but do be aware, just as we finish this lesson up here, that at higher altitudes, the gravity field is reduced. And it's not very convenient to be using this mg calculation that we've got here to try to find forces of gravity on satellites if they're far from the Earth's surface, because it's just a hassle to calculate that g only to use it once. So typically, we will be finding forces of gravity using the full equation g m1 m2 all over r squared. And that's going to be in the next lesson when we start to take a look at planet orbits.